Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement polynomial regression from scratch. We'll use only basic Python libraries like NumPy for this exercise. Recall that polynomial regression is a linear regression with an additional step of polynomial transformation. So we are given examples in form of features. Then we perform polynomial transformation on these features and then apply linear regression on the transform feature set. We'll reuse linear regression class that we implemented in the linear regression model Colab. In this Colab, we'll specifically implement polynomial transformation function and a few helper functions for generation of training data with nonlinear relationship between features and labels. We will generate examples with single feature and a single label. We will visualize training data and model fitment. We will use polynomial transformations of different degrees for modeling relationship between input features and the labels. Each degree results in a new polynomial model. Thus, we have multiple polynomial models from which we need to select the best performing model. We have implemented model selection scheme towards end of this Colab. We will record this Colab in two parts. In the first part, we will implement polynomial transformation function and the data generation part. In the second part, we will implement or we will apply polynomial regression on the nonlinear data that was generated from the data generation function and also study the model selection. Let's begin. We start by importing essential libraries and we also borrow the code from the linear regression Colab for the linear regression class. This particular class has been brought in without any changes. As we said, polynomial regression is nothing but linear regression with polynomial transformation. So polynomial transformation is a key step in polynomial regression. Let us study polynomial transformation in detail. Polynomial transformation is a two-step process. In the first step, we generate combination of input features of length 0, 1 all the way up to m, and m is the degree of polynomial that we wish to generate. Then we perform multiplication between different features to obtain the new features. So let us understand this with a few examples. Let's say we have a single feature x1 and we want to generate polynomial transformation of degree small m. So the polynomial transformation, after doing polynomial transformation on this feature, we will get new set of features which are like 1, x1, x1 squared all the way up to x1 raised to m. You can see that this x1 was the original feature and there are all other features that were derived through the polynomial transformation. In order to derive these features, we first generate combinations of input features of different lengths. So for example, length 0, we have feature 1. For the length 1, we have the input feature itself. We generate the feature combination of length 2 in the following manner. So we have feature x1, so we have x1 comma x1 is a combination of length 2. Then for generating combination of length 3, we essentially write the same feature 3 times, and in order to generate combination of length m, we write the same feature m times because we just have a single feature over here. The second step is to take the product of elements in each of this combination. So we have 1 which is length 0, we have x1 of length 1, then for length 2 we had a combination which is x1 comma x1. So we perform the multiplication between these two terms x1 into x1 to get x1 squared. Then for length 3 or for generating third degree polynomial, we multiply these three, the combination of length 3. So we get x1 cube and all the way up to x1 raised to m. Now let's try to see how we can generate the second order polynomial for two features, say x1 and x2. Since we are talking about second order polynomial, we need to generate combinations of length 0, 1 and 2. So the 0 length combination, essentially you get 1. For length 1 combination, we have two combinations here. One is x1 and then the second is x2. So we have 1 for 0 length x1 and x2 for length 1. For length 2, we have we can generate different combinations, which is x1 comma x1, x1 comma x2 and x2 comma x2. So these are three possible combinations of length 2. Now what we'll do is we'll take product of elements in each of these combinations. So you can see that we will copy your 1, x1 and x2. x2 is missing over here, but x2 should have been here. Then x1 squared, x2 squared and x1, x2. Now let's generate third order polynomial from two features x1 and x2. So again, we'll generate all the combination just like the second order polynomial all the way up to length 2. So you can see that the 0 degree, first degree and second degree combinations are exactly same as the previous example. Now we'll be generating the third degree polynomial. For generating third degree polynomial, we need to generate combinations of length 3. So we will take one feature x1, we'll repeat it 3 times, then we will repeat it 2 times and take x2, then we will have 1 x1 and 2 x2s, and finally we have 3 x2s. We can take product of elements in each of this combination to get the third order polynomial transformation for these two features x1 and x2. So the transformation will have new features which are 1, x1 and x2 were already present, x1 squared, x2 squared, x1 cube, x1 squared, x2, x1, x2 squared and x2 cube. So these are some of the new features that are generated for the third degree polynomial transformations of feature x1, x2. Let us implement this procedure in Python code. So for that we'll need two libraries, itertools and functools, and we'll generate and we'll implement two functions. One is get combination and second is compute new feature. Get combination function generate combinations of different lengths for particular degree, right? So if degree is 2, we'll generate all the combination of length 0, 1 and 2. If degree is m, we'll generate combinations of length 0, 1, 2 all the way up to m. And in compute new feature function, we simply perform multiplication of features in each of the combination. So this reduce function, for an example, let's say we want to perform the multiplication between two elements in the combination, and let's say element has these 5 values 1, 2, 3, 4 and 5. So the way the way it calculates is it first performs multiplication between 1 and 2, then the resulting number will be multiplied with 3, the resulting number will be multiplied with 4, and finally the resulting multiplication of first 4 numbers will be multiplied with 5. So that's how this particular function works. So let us run get combinations on a few examples, and we'll also run compute new feature for the combinations that are generated from get combinations function. So in the first example, we'll generate a combinations of length 3 for a single feature x1 which is set to 1. So it generates exactly one combination containing 1, 1, 1, and the compute new feature will perform the multiplication of the individual elements in this computation. So we get the value of 1 over here. Let's run another example with two features x1 equal to 2, x2 equal to 3, and we want degree 3 or length 3 combinations. So here the combinations that are possible is 2 copied 3 times, 2, 2, 2, 2, 2, 3, then 2, 3, 3, and 3, 3, 3, and we perform the compute new feature operation, or we subject or we input each of this combination to compute new feature function which performs the multiplication, element wise multiplication, and here we get new features which are, so 2 into 2 into 2 is 8, 2 into 2 into 3 is equal to 12, then 18, and then finally 27. So let us look at one more example where we will generate length 4 combinations from again two features 1, 4. So you can see the length 4 combinations that are listed out here: 1, 1, 1, 1, 1, 1, 1, 1, 4, 1, 1, 4, 4, 1, 4, 4, 4, and all 4s. And then you can also see the multiplication, element wise multiplication, which is 1, 4, 16, 64, and 256. So these are the new features, new fourth order polynomial features that can be generated from the given input. So with this, I hope you are clear about how the combinations are generated and how compute new feature function works. So let us combine both these functions to implement polynomial regression, or to implement polynomial transformation, which is a key step in polynomial regression model. We have adopted this implementation from pattern recognition and machine learning books GitHub library. And so what we do is the polynomial transform function receives the input, which is a feature vector. Then we have the degree, which is desired degree of the polynomial transformation, and then we have one more flag for logging. So when we run polynomial transformation with logging on, we get a bit more information about what combinations are being generated and how the new features are computed. So if the input feature vector is one-dimensional feature vector, we convert that into a feature matrix. Then we transpose the feature matrix. Then we populate ones as first feature for each example. So if this particular feature matrix has n examples, we'll be copying ones n times, once for each example. And then, so you know that whenever we want to generate polynomial transformation of a certain degree, what we do is we first generate combinations of different lengths, essentially 0 length, length 1, all the way up to length equal to degree. So we will first generate this combination. So we run this outer loop, and for each length we generate the combinations, and then we compute new features based on these combinations. And finally we will we will have the new features in this particular features array, which we will transpose and return. So that's how we'll get our polynomial transformation of the given feature matrix. So let us apply polynomial transformation on few examples and see what it does. So let us say we want to perform polynomial transformation of degree 3 on the input feature vector, which has a single feature x1 with value 2. So since this is one dimensional feature vector, we first convert that into a feature matrix, and then we generate combinations of different lengths. So combination of length 1, length 2 and length 3, because we want third degree polynomials, so we will generate all combinations 1, 2 and 3. The zeroth, for 0 degree transformation, we do not generate any combinations because we copy them beforehand in this particular statement. We copy once into feature array. We do not get that in this particular loop. So the first combination of length 1 that was generated has element 2, and if we perform multiplication, so there is no other element, so it becomes 2. So length 2 combinations are 2 and 2. We perform multiplication to get 4. Length 3 we have 2 repeated 3 times, and the multiplication is 8. So the feature matrix has, the transform feature matrix has 4 elements: 1, 2, 4 and 8. Let us take another example where we will perform polynomial transformation of degree 2 on the input features 2 and 3. So now this is a feature vector that we give as an input, but this polynomial transformation function first converts that into a feature matrix. So it converts it into a feature matrix with 2 examples with a single feature each. So x1 is the input feature. For the first example, value is 2. For the second example, value is 3. And now we have to perform the second order polynomial transformation. So we need to generate length 1 and length 2 combinations. So the length 1 combination will have the input itself 2 and 3, which will have essentially the product is for, because there are individual terms, right? So the product of the term with itself is the same element, which is 2 and 3. For the length 2, we will copy the input 2 times because we need the second order polynomial. And now what will happen is that there will be element wise multiplication that will happen. So this 2 gets multiplied by this 2, this 3 is multiplied with this 3, resulting into 4 and 9. So the polynomial transformation for the given input is 1, 2, 4 and 1, 3, 9. So you can see that there is a single feature 2 which got transformed into 1, 2 and 4, and the single feature 3 got transformed into 1, 3 and 9. Let's perform one more polynomial transformation with 2 features x1 and x2, and again there are 2 examples in the feature matrix, and we want to perform degree 2 transformation. So as you know, we have to generate combinations of length 1 and 2, and remember the 0th order polynomial we copy into the feature array before the loop. And now the combination, the length 1 combinations are, so 2 and 4, because see, we first transpose this feature matrix, and that's why we have 2 and 4, which are the first elements or the first features of example 1 and 2. Then we have 3, 5. So because these are single elements, we copy those elements as they are. In order to generate the second degree polynomial, we'll generate length 2 combinations. So we have 2, 4 and 2, 4. We'll have 2, 4 and 3, 5 and 3, 5 and 3, 5. These are 3 length 2 combinations that can be generated. And then we perform element wise multiplication. So we get 2 into 2 equal to 4, 4 into 4 equal to 16, and then here we get 6 and 20, here we get 9 and 25. So we finally have 1, 2, 3, 4, 6, 9 and 1, 4, 5, 16, 20 and 25. So we have ones written here, these are 0th degree polynomial. Then we have the elements copied as they are, which is 2 and 3 and 4 and 5 in the second case. Then we have square of 2, then square of 3, and then multiplication of 2 and 3, which is 6. And same thing happens here over here, square of 4, square of 5, and multiplication between these two elements, which gives us 20. Let us generate a polynomial transformation of degree 3 for the same input as above. So we have already seen this particular part. So now we'll focus on generating length 3 combinations. So length 3 combinations can be generated by copying the elements as they are 3 times, which is 2, 4, 3 times, then 2 and 2, 4 2 times, and then the next element, which is 3, 5 second time. And another one will be 2, 4, 3, 5, 3, 5, and then the last one is 3, 5, 3, 5, and 3, 5. And now we'll perform element wise multiplication, which is 2 into 2 into 2, which is 8, 4 into 4 into 4 is 64. Then 2 into 2 into 3, we get 12, and 4 into 4 into 5, we get 80, and so on. So the third degree polynomial transformation for this input reads something like this. So we get degree 0, which is 1, elements themselves are 2 and 3, the square of the individual elements, which is 4 and 9, then multiplication between these two elements is 6, then we'll have cubes of individual element, which is 2 cube is 8 and 3 cube is 27, and then we'll have x squared, x1 squared x2 and x2 squared x1. So 4 into 3 12 and 9 into 12, 9 into 2 is 18. So this is how the features are generated, the third degree polynomial features are generated for this input, and you can verify the same thing in case of the second example. So finally we'll generate a 0th degree transformation for the input of a single feature, which is x1 and the value is 2, and you can see that it simply returns value 1 because we just want a 0th degree transformation. So hope this makes it clear how polynomial transformation works. In the next video, we'll generate the nonlinear training data and apply it and apply polynomial transformation to learn the relationship between input and the output.